I think we're going to go ahead and get started on today's 6th Ivan Roundtable Workshop for NMR Research. Title for today is Adequate. And at this time, I'm going to turn everything on over to David Rice.
Well, welcome again to the 6th meeting. And Eric has said it all. So before we get started, let me turn things over to John Webb, our sponsor.
Well, thank you, Dave, and good morning, everyone. Good afternoon, good evening, wherever you may be. We've got yet another great meeting set up for today. Gary Martin has some very interesting topics to lead us through, and very thankful for that. This is actually meeting number 11, I think workshop number 6, but virtual Ivan meeting number 11. And wow, they're just seem to be continuing as popular as ever. It looks like we've got over 100 participants today, and very glad for that. Got really interesting announcement for you shortly. I'll hold on to that for a couple of minutes. I think that's going to make everyone very excited once they hear. But just a couple of words on our sponsors before we begin. MR Resources, of course, has been around for 35 years at this point, and still servicing and repairing and bringing back to life quenched magnets and selling reconditioned systems. By the way, they're always on the lookout to purchase any used NMR spectrometers, shielded magnets you may have. Get in touch with them. And our co-sponsor, Q1 Instruments, we've got Don Bouchard with us. And Don, could you give us a little bit of information on Q1, please?
Q1 designs and manufactures complete spectrometers from 400 to 600 megahertz with features for routine use in the research laboratory. Want to upgrade an older system? Q1 can retrofit AS and UltraShield magnets with complete upgrades, including automation, for less than you think. Q1 offers NMR instruments with excellent performance at an unbeatable price. Q1's operating environment is Spin Studio J. Spin Studio J has a plug-in-based paradigm for extending virtually any capability, either internal to the spectrometer or externally, via Java-based tools for data acquisition, analysis, and connectivity. Spin Studio J is a multi-language platform with hierarchical data format files with validation and exportable to third-party processing platforms. We will soon release a new NUS plugin based on the deep learning algorithm published by Shaman University and exclusively licensed by Q1. This advance uses an iterative process of removing artifacts by a dense convolutional neural network for data consistency to speed data acquisition by a factor of 5. Want to know more about our probes, consoles, and complete systems? Please contact us for a no-risk remote demonstration. Thank you very much.
Thank you, Don. And Q1 Instruments, up-and-coming company, and very, very good line of equipment. Never mind all that. Let's get to a really fun announcement, I think. This year's ENC, of course, is going to be virtual. Begins on Monday this year, not Sunday. Begins on Monday, March 29th. And the Ivan Group is going to spend the day on Sunday, March 28th, from all Eastern time, 10 a.m. to 3 p.m. Eastern time, at what we're calling Ivan Live from Asilomar. Meeting's going to be virtual, but well, we're going to leave you folks a little bit of suspense. There are going to be some live components. Again, Ivan Live from Asilomar on the pre-ENC meeting, Sunday, March 28th. And Krish, maybe you can tell us a little bit more about it, if you would, please.
Thanks, John. We have a lot of interesting, in addition to the fun stuff, we also have a lot of interesting science part of it for Ivan Live from Asilomar. We have a full agenda. We haven't put together the formal time and the lineup, but as you can see on the slide, there is a large number of people are giving talks on practical as well as science-based topics. Look out for your email or visit ivanmr.com to look at our agenda. It should be posted very soon, meaning within a week, probably by the end of this week, or at least early next week. In addition to the information on the SLOMR, Ivan from SLOMR, I also want to say a little bit about what is coming down the pike with respect to this this workshops. The next one, I believe, is a topic on polymer NMR by Bob Bernal. That's on March 18th. So this is exactly 4 weeks from now. And then it's followed by a series of further topics, including craft, non-uniform sampling, advanced and principal component analysis, quantitative NMR, pure shift, and so on and so forth. So keep up. We are keeping up with it. We are almost, our agenda is full, almost down to September, October timeframe. If you have any ideas that you want to share with us on potential topics, please reach out to me. I will see if I can schedule you further down. So with that, I will pass back to Dave Rice to continue this today's meeting.
Again, Ivan live from Asilomar. Please do join us. Going to have great speakers, fun and informative day. And there's going to be a lot of really good prizes. So anyways, Dave, to you, and please get things going if you would.
Okay, great. So our meeting will have the usual format. We're going to have 4 speakers led by Gary Martin. And we'll probably go to the top of the hour with the agenda. And during that time, keep yourselves muted and video off so we can see the panel. And then we'll open it up to questions. And if you have questions during the talks, put them in the chat. And we're monitoring the chat so that you can, and so that we can answer those questions during the talks. So without further ado, let me turn it over to Gary Martin.
Thanks, David. I'd like to thank everybody for coming today, first of all. Today's topic is using homonuclear carbon-carbon correlation with variants of the adequate experiments. I want to thank our speakers, first of all, Josep Sauri from Merck, Joonseok from Yale, and Ron Crouch. And let's think about this for a minute. Before I turn this over to the speakers, I'm going to say a few words about why you might want to use an experiment like adequate. I'm sure everybody in the audience is familiar with the usual ensemble of 2D experiments, COSY, HSQC, HMBC, sort of like doing synthesis where you do methyl ethyl butyl futyl when you're synthesizing things. Sometimes people, and less often, use LRHSQ-MBC or H2BC to identify carbons. H2BC is good if you're protonated vicinal, have a protonated vicinal carbon. All of these experiments are useful in that they only require one C13 in the structure of your molecule. In contrast, if we call HSQC a 100% experiment, in comparison, HMBC or LRHSQ-MBC is down by a factor of 4. When you compare that to adequate, you're down at the 1% range. So the comparative sensitivity, as shown here, Josep will talk a little bit more about in a few minutes. I don't want to steal his thunder, but there you go. I want to take a quick look at why you'd want to do this. This is a paper we did collaboratively with Emily Meevers and John Clardy at Harvard a few years ago. When John related the saga of the elucidation of this structure at the ASP meeting in Madison, Wisconsin a couple years ago, here's what they had after 3 years of playing with this compound on this slide. COSY, HSQC, that's what you had in terms of structural features. If you go to the ACD NMR database, they could generate the 2 components that are shown in blue. They fed all of the data for this C28 compound into the ACD structure elucidator, which is a case program. It failed to provide the structure of homodimericin in a reasonable position. And by reasonable, you're talking top 5 or so candidate structures. Without adequate data, the best the program could do was to put the structure in the 16th position out of over 400. You're not going to trust something that's that far down in a case program if you've never used it. Part of the problem, there's the structure after it was elucidated. In an HMBC spectrum, everything couples to everything. So a priori, how do you tell if something's a 2-bond, a 3-bond, or even a 4 or 5-bond correlation? If you were to think about using LRHSQ-MBC, what's shown in on the structure in the right in green, these are the correlations that LRHSQ-MBC gave you in addition to everything shown in red on the left structure. The 40 Hertz optimized 1.1 HD adequate experiment gave us the correlations that are shown in red on that partial structure. Once a good portion of the hexacyclic core of the molecule was assembled, the HMBC data were rendered interpretable. There's the correlations that put the rest of the structure together. From the partial structure, you can go to the final structure. The molecule has 8 chiral centers, 4 of them non-protonated, which adds yet another layer of complexity, which required the use of heteronuclear coupling constants and anisotropic NMR methods that are a topic for another day. What was interesting about this, and I'm going to brag about Josep, from when we got the sample of this molecule in hand to when Josep had a proposed structure was a week using the adequate experiment. When you feed the adequate data to the case program, the correct structure comes out first in the output list. And the carbons that are shown in blue on this structure, there are 11 contiguous non-protonated carbons in the structure, which makes this a really challenging structure to put together. And one of the presentations a little later on today by Joonseok is another such example of a molecule there that they had to resort to adequate to solve. Before we get to everything else, I want to thank Josep, Joonseok, and Ron for agreeing to present. Also need to acknowledge my colleagues in the NMR group at Merck, without whom a lot of what you're going to see today never would have been accomplished. And this is Chris's favorite slide of this presentation, Onward Through the Fog. And with that, I'm going to pass the baton. And Josep, you're it.
Thank you, Gary. So yeah, thank you. The introduction made by Gary was very nice, and you will see some of the things he talked about. I will briefly mention. In this presentation, I would talk about new variants of the adequate experiments. And essentially, this is something you have seen already. I want to introduce here one of the main problems of the 1.1 adequate experiment and the 1N adequate experiments, which is the 2 main experiments of this family of experiments. And this is the low sensitivity of these experiments. And this is, again, because we are looking at correlations that are based on carbon-13 coupling constants. And so the fact that due to the low nitrile abundance of carbon-13, these experiments will be very insensitive. If you assume HSQC as 100% sensitivity with 2 scans, then you realize that the HMBC is 1/4 of sensitivity roughly, and 1.1 adequate is 1% of that, and 1N adequate is 0.25% of that. So very insensitive experiments, but as you will see, they are actually quite elegant, and they provide a lot of information. So I will describe in the next slides what the main experiment does and some of the variants that we have developed over the years. This presentation is based on actually in a book chapter that we published in 2019, and it talks about all these experiments here. One of the main modifications that we did to the 1,1 adequate and the 1N adequate is that we incorporated what is known as homodic coupling techniques, and this provides a sensitivity boost in these already very sensitive experiments. I will then talk about a version of the experiment that allows you to distinguish 1,1 carbon-carbon correlations from 1N carbon-carbon correlations in the 1N adequate experiment. And finally, I will talk about the J-modulated 1,1 or 1N adequate experiment, which allows us to measure this color coupling constant between two carbon nuclei. So first of all, as I said, I want to introduce the HD version of these experiments. We published this back in 2015, yes. And essentially what we did is we took the idea of the pure ship HSQC, which uses this bird decoupling approach, in which essentially this element in the pulse sequence allows us to remove the proton-proton coupling constant from the final multiplex. But you will see that unlike the HSQC, this homodic coupling does not work for all the spin systems in the 1,1 and 1N adequate. And this is because we are looking at the correlations, again, between two carbon-13s. Essentially, what the bird decoupling building block does is allows us to distinguish protons that are attached to carbon-12 from protons that are attached to carbon-13. And so we have to consider several possible scenarios here. If we talk about the 1,1 adequate, which essentially provides correlations between the adjacent carbons, 1 bond, carbon-carbon, here we have two potential scenarios. One in which we are looking at correlations between proton attached to a carbon, and the adjacent carbon is a quaternary carbon. In this scenario, the homodic coupling will perform well, because here we are able to remove the proton-proton coupling constants between the carbon-12 and carbon-13. But if we look at another spin system, which is protonated carbon adjacent to another protonated carbon, here homodic coupling will not work in the same way. We will still able to remove proton-proton coupling constants between carbon-13 and carbon-12, but not the mutual bisinol coupling constant between the two carbon-13. And so everything will collapse up to a doublet, because the large geminal coupling constant cannot be removed. So here is what you get from the spin system in which a quaternary carbon is involved. Essentially, there is a sensitivity improvement. Here we've shown the results using ibuprofen as a tool compound. And then in the spin system where involves two protonated carbons, the sensitivity improvement is essentially, there is no sensitivity improvement in this case. Still, it's very important that the sensitivity improvement is the one that you achieve in spin systems in where you have a quaternary carbon. Because for protonated carbons, you have already conventional 2D NMR techniques that can provide very useful information. And if you look at the 1N adequate, then since we are looking at correlations between long-range carbons, here the homodic coupling technique will not decouple the two protons that are attached to carbon-13, but they are now very far away. They are going to be like 4 bonds, proton-proton coupling constant, very small. And in practical terms, what you get is a sensitivity improvement similarly to the 1,1 HD adequate. So this was very nice experiment. We applied this to several compounds over the years, very complex natural products compounds, like homodimerizine. You have seen this from Gary. The original reported structure of phytosterolepin was reported in 1993, and it was wrong. We were able to revise the structure with the 1,1 HD adequate experiment. And another shown compound here, very complex, was colomidine A, in which we applied the 1,1 HD adequate successfully as well. Now, I want to talk about the inverted 1 JCC 1N adequate. Now, we are talking about 1N adequate here. So we are getting long-range carbon-carbon correlations. Unfortunately, here in this experiment, not only the N-bond correlations between carbons show up, but also the 1,1 carbon-carbon correlations. Now, this experiment, what it does is, somehow what we're doing is editing the multiplets that belong to the 1 JCC from those that belong to the NJCC. Essentially, similarly to HSQC with multiplicity editing, in which we are able to distinguish the multiplicity of the carbons. But the approach here is different, and it's based only on the difference between the 1JCH and the NJCC. Sorry, the 1JCC and the NJCC, because the magnitude of this coupling constant is quite different. So we take this as an advantage, and we essentially, what we are doing is conventional experiments that everything shows up with the same phase, but by doing this inversion of the 1JCC, now the 1JCC responses will show up with opposite phase with respect to the 3JCC, and we are able to distinguish one bond versus N bond, which is very, very nice. Now, there are some limitations associated with this experiment, and depending on the, on the magnitude of the coupling constant, some will not invert the phase as we expect. Essentially, here I want to introduce what's the problem of the single optimized experiment versus the dual optimized experiment. The single optimized experiment provides inversion for a wide range of coupling constants, but there are some island of coupling constants that are not going to be inverted as we should expect. So for instance, if we optimize the experiment for a 40 Hertz in the 1JCC and 7 Hertz in the NJCC, there will be no inversion from these different ranges of coupling constants, essentially from 32 to 35, from 58 to 63, from 71 to 78, and everything above 80 Hertz will not be inverted. So that's a problem, actually. So they came up with another version of the experiment in which, instead of using the single optimization, they use a dual optimized experiment. Without going into too much detail here, what we are doing here is we use two amplitude transfer functions, we add them up, and then what we have is this brute race, which is the sum of these two, green and red. And what we achieve is a very universal broadband inversion. Now everything between 0 from 82 Hertz will be inverted. And this is very useful. Next, what we did is, to this dual optimized inverted 1JCC, one inadequate, we incorporated the homodecoupling technique, which provides a sensitivity improvement. Here, what is shown is a comparison of the conventional experiment, which provides in red correlations that are 1 bond CC, in black N bond CC, compared to the homodecoupling experiment here, and slightly shifted to the right is the conventional experiment. You can see the conventional experiment shows up as triplet, and here it's a doublet, and this is how the HD works. And for N bond correlations, everything collapses up to a singlet. So another example is shown here using this model compound perthenolite as an example. Then we also did some of this HD methodology to the J-modulated adequate. The J-modulated adequate is another variant of the experiment that allows us to measure coupling constants. Coupling constants 1JCC and NJCC have been shown to provide useful stereochemical information. And here the J-modulation, what it does is essentially splits up along the F1 dimension the cross peak, and this splitting reports about the carbon-carbon coupling constant. And then if we apply the homodecoupling, we can simplify multiplets from doublets to singlets with a sensitivity improvement. Here is shown the performance. HD provides a sensitivity improvement, as you can see, compared to the conventional experiment. And a very nice example that of this J-modulated one and HD adequate is shown here. This very complex stereochemistry problem. It was not possible to assign the E or Z isomer based on proton-detected NMR experiments. Chemical shifts were also very ambiguous. Not even DFT were very helpful here. Instead, if you do an analysis based on carbon-carbon coupling constants, you can realize that you can do the assignment with combination of DFT calculations and assign this as the E isomer based on this 3-bond carbon-carbon coupling constant. Finally, I just want to mention, to finish this up, that this J-moderated HD adequate, which needs a lot of resolution along F1 to resolve the coupling constant, can be combined with non-uniform sampling approaches. And we published this paper, and it shows that NUS can be applied up to a 50% with very good results. And you can either use NUS to get more sensitivity or more resolution in the same experimental time, or even in half of the experimental time, achieve the same data that you would without no NUS. And with that, I just want to thank everyone for listening, and I'll be happy to answer any questions at the end.
Thank you so much, Josep. There was one question in the chat. We can certainly make available the pulse sequence code. This is from Robin Stein to everybody for the Brooker experiments that were developed. I know Ron has them available for the JEOL instruments, and I think Ron also probably has copies of some of these for variant instruments, or you could certainly reach out to Krish on that one. Okay, so what I'd like to do now is to pass the baton to Joonseok, who's going to talk to us about carbocyclonone.
Okay, thanks for the nice invitation, Gary. And then, I'm thrilled to, share the results that our group has been done. So I want to talk about some molecule called carbocyclonone, which really required adequate experiment. So this experiment, it was indeed, as manifested by its name, it's an adequate experiment for our purpose. And then this carbocyclonone compound has been purified from the bug that called the Photorhabdus. And I want to talk about a little bit about background about that bug as well. Okay, without further ado, let's get started. Okay, so I define myself as a natural product chemist, and then NMR for us, NMR experiments are crucial and then very, very important. So 1D and 2D NMR parameters are really being routinely employed every time, every day, like COSY, HSQC, HMBC, and all that. But the problem is that we just maybe some other natural product chemists could understand, but for me, personally, I do lack of some understanding of how NMR experiments are working. So, for example, parameter change or proper scan numbers and all that. So a good example with that is HMBC. So HMBC can be shown. It can show the a 2 or 3 bond away correlation from proton to carbon, or more away correlations in certain geometry according to Gary. So 6 bond away as well. But sometimes 2 and or 3 bonds are really arise some ambiguity to us. So if we have a proper structure and we don't see some proper HMBC, then we have to question ourselves whether this is caused by the wrong assignment or wrong parameter setting for the NMR experiments, that kind of stuff. So to tackle that type of problems, we have to use some other advanced NMR techniques, but sometimes we just don't know how to do it properly. So we have to reach out to the professions, like Gary or Krish or Spin Site as well. So this is very, very helpful forum for us to continue our study. So for example, H2BC is it can show the 2 bond away proton, carbon from a proton using the magnetization start from here to cause transfer to detect the 2 bond away proton, but still it does have some caveat because cause correlation, if the 2 bond away carbon is quaternary, there's no way for you to detect the correlation that you're looking for, right? Which contrasts to 1-1 adequate that we have been seeing from a Jocep's presentation really deeply and thoroughly. So, but it does show the 2 bond away carbon, but still, as he mentioned, it suffered from the very low sensitivity. Okay, so we do need to set up nicely, and then carbocyclonone project will be a good example, and then which I'm going to talk about later on. Okay, so before we just go into more deep about how NMR has been worked for our group, I just want to quickly touch base the general workflow of our lab. So our lab we used to work on the some understudied strains like Photorhabdus, Temperata, A. symbiotica, Boviani, and all that. Also, we also do some genetic tools to do some overexpression of a certain gene cluster and all that. And then using the different media, we try to think about, try to detect some unique ions in the Q-top analysis, which could be followed by the comparative metabolomics. So medium, mutant, or depending on the design of your experimental system, this could be like, overexpressed strain and all that, or like wild type. So we try to target some unique features that can be, exclusively detected in the your experimental design. Like for example, like wild type here could be like a good candidates, and we kind of try to target some like couple of them, and then large cultivation to get to the NMR structure purification using HPLC and NMR and configuration analysis. Yeah, so so in our group, the number step is a crucial step. So that's why I'm working here as a postdoc in our group. Okay, this is the carbocyclonone structures. So Stilbene dimers from the Photorhabdus luminescens. So as you can see that at the first time, it has been purified as a racemic mixtures. And then Stilbene dimer, you can see that the Stilbene is a very famous compound made by the Photorhabdus. And then we were able to detect this type of molecules in our study. Okay, before we talk about some NMR stuff, I just want to give you a little bit heads up about how Photorhabdus luminescens interesting life cycle. So there are three tripartite relationship. So three entities are shown here. So first one is nematode here, and then this is the Photorhabdus that we have been growing. Okay, so this is colonized in the nematode guts, and then nematode and Photorhabdus are friends. They are a symbiotic relationship. And then once the nematode burrows into an insect as a prey, the nematode will regurgitate the Photorhabdus in the gut through their mouth, and then the Photorhabdus quickly colonize the insects. And as you can see, that this is like light, so that's why it's called luminescent. So they are all the this bug, and then this bug is like very, very hostile towards the insect to kill it. So it will produce like deadly secondary metabolites to kill the insect, and also like ward off other competitors so that nematode can secure their prey for their growth, development, and proliferation as well. And once the insect is dead, and then they are full, then they emerge from the cadaver of insects, and then try to this is nematode, and in here there are Photorhabdus reside, and then they find another like prey and so on and so on. So it's like very interesting life cycle. Okay, so we did some genetic analysis, and then we realized that PLU, so Photorhabdus luminescens, 1886 gene cluster, gene synteny, encodes the carbocyclonone. We realized that. And then just like the homodimerism, correct, like that Gary talks about at the beginning, we couldn't really finalize the this piece of structures at the end. So the conventional HMBC doesn't show correlation. So our group has been routinely using long-range HSQMBC under the Gary's advice, and then does show the correlation. But just like Gary mentioned at the beginning, even if it showed some correlations, but we just don't know how far that carbons exist from the proton of interest in here. So we thought, one etiquette could be very useful. So I went down the core, our core, and then load adequate. And then it showed the 45 Hertz coupling constants optimization like as a default value. And then of course, we ran it and then we didn't see the correlation, anything. And then I reached out to Gary at that moment. So Gary's, told us that, oh, if your cyclopropane is correct, you're barking up the wrong tree. You have to change the coupling constant. He didn't say they're barking up the wrong tree at that moment, but I'm just saying, so a coupling constant should be modulated. So he gave us like a long list of typical value for the carbon species. So we are falling into this one. So I'm going to talk about the results on the following slide. And at the same time, Dr. Bill Reynolds at University of Toronto also give us a similar advice at that moment. I really appreciate for these two, for us like heroes, Okay, so this is how it looks like. So coupling constant is, modulated 50 Hertz. And then Gary also mentioned about quaternary carbons are reaction time is very long. So you have to think about the, changing to the 3 seconds, So we just use a regular default setting, and it only shows the proton to C3, which is expected, but we don't see anything in here. This thing, and this information is also acquired from the COSY and H2BC already. So this is useless for us. But if we change it 10 Hertz and after overnight experiments, it showed beautiful 2 peaks. I was very, very happy at that time. So my boss was really happy. So I feel like this is really, help me to be recognized in the NMR person in our group, but through the help here and there. But yeah, as you can see, that proton H1 to C1 and C2 are definitely shown. So we were confident that first one, we finalize structures, and then we do realize that cyclopropane structure is existing there. And also this explains why our conventional HMBC doesn't work, but long-range HSQMBC is working. So also, Dr. Bill Reynolds explained that as well, on the spin side discussion later on. So all riddles have been solved. Okay, so after that, we decided to do the X-ray crystal. So as I mentioned at the beginning, structures are purified as resin mixtures. So crystal has been, grown as a resin mixture. So we were able to reaffirm the NMR structures. And then, the color separation was done by some company in Princeton. So they did a really great job for us. And then we did some ECD calculations so that we were able to find the plus and minus enantiomers, and then do the ECD calculation to finalize all the optically pure compounds at the end. Okay, so I may have to, just like the chats that we just saw, the variants, the software code, it's really hard to get, even Hadlock and then HD adequate that Josep talks about, and gen modulate adequates. So we have read about this type of beautiful, fancy experiments in the high profile journal, but we just don't know, how to get or where to get. So that's something that, we need to get some help from here and there. So hopefully, this software library could be available for us so that we can freely use for our routine NMR experiments. Okay, so I'm gonna end with my acknowledgements. Crawford Lab, Jace Crawford, who's my boss, and then Hyunbong Park and Tyler Goddard. They are the lead author for the Carbocyclonones paper, and I just helped them to do some NMR experiment and ECD calculation and all that. And then of course, Gary Martin, and then Krish. I also thank him And SpinSci now Ivan NMR user group. I thank you. And then this is our group. Yeah. So if there is any question, I will be happy to answer. Thank you.
Thanks, Joonseok. Very interesting talk, and certainly an interesting challenge structurally to assign the structure. It's nice to be able to resort to X-ray just to confirm the NMR instead of using X-ray to justify how to assign the NMR.
Yeah. Right. That's, we are very, very proud of that. So we're praying that X-ray crystal is correct.
And at this point, what I want to do is pass the baton to Ron. We've been talking about proton-carbon-based experiments where you're doing an initial proton-to-carbon transfer and then a carbon-to-carbon transfer. So it's an out-and-back experiment that's proton-detected. One of the inherent problems of late is that the pharmaceutical industry has gotten to be very fond of sticking fluorines in things. And then there's the folks at DuPont and Chemours who are making polyfluoro and perfluoro everything. And these things are getting into the water table, which prompted us to start looking at, okay, if we can do this with proton carbon, why not fluorine carbon? And with that short introduction, it's all yours, Ron.
Thank you, Gary. So thank you very much for the opportunity to speak. And what I'm going to try to do is try to convey a very small part of things that are going on. Here we go. As people talked about already, that part of the reason that adequate becomes so very interesting, particularly 1.1, is that in many cases, HMBC tends to have an overabundance of information. So this is an example from an app note long time ago that I did on voriconazole. And at the time, I was very excited to see all these fluorine-carbon correlations done with a 20 Hertz optimization in a GHMBC-AD. And while extremely useful and powerful in the case where you're using the HMBC to confirm a structure and make assignments, when you have an unknown structure, as we've seen, it could be a source of confusion. So if we look at a simple perfluoroaromatic compound, you see exactly the same trend as what's going on here. And for instance, let's see if I can get a laser pointer. Now I've got it. What we see is, for instance, for F2 and F6, they essentially both couple every carbon in the molecule. With the exception of the nitriles, there's a differences. For the lone guy down here, F5, which is away from the aniline dimethyl, it couples everything in the aromatic ring, but not that. So we're too information rich. And this was acquired with a 30 Hertz HMBC optimization. So to understand the situation, let's do some measuring of coupling constants. What we all know is that things like IPAP methodology to measure heteronuclear coupling constant is fantastic. And in fact, it works really very well with fluorine carbon as well. But in a case like this with a simple perfluoro with 3 fluorines, it's extremely efficient to do a carbon spectrum and simply acquire 3 carbon spectra with 3 selective fluorine decoupling. So in this particular example, we've decoupled each of these 3 fluorines and recorded the spectra, and we see that, in fact, this nice double of the doublets is a pair of 19.6 Hertz couplings from that pair of methylenes. So we can continue this and just simply annotate other carbons, look at other carbons in the same experiment, and from it we can deduce every coupling constant fluorine carbon in this molecule in just a very few minutes of time. Now, so here's a table of it. And I think I saw that Roberto Gil was here, so I quickly edited my slides and I changed one of the J's in the table to not be italicized, just for his editorial pleasure there. So we have all these fluorine carbon couplings, but what about carbon-carbon couplings, which is very important if we start getting into adequate? Well, if you've got access to a nitrogen cold probe, then it's pretty easy to acquire inadequate experiment efficiently if you've got a little bit of material. This is a 53 milligram sample. You can acquire a 2D inadequate in 4 to 5 hours. You can acquire a really nice one overnight or a really, really nice one over a weekend. So this is a fluorine carbon. As an aside, I will say that these days I'm using bus decoupling for fluorine because it has a tremendous nice attribute. It was originally intended for ultra high field decoupling, but it's really nice for fluorine because the internal pulse widths are very short, which means it can deal with the really huge fluorine carbon coupling constants, in particular with one bond. So in bus, peak power is very high, but average power is very low. So if we take a look at the inadequate spectrum, it's separated up into 3 columns. Here, we like just for C3 and C4, what we see, of course, are doublets. And if we put a high resolution 1D inadequate on top, we can quite precisely measure all the carbon-carbon coupling constants in here. And we see that they are generally large compared to any proton-carbon system. In particular, the nitrile, we're looking at 94 hertz. The C5 to C4 is also large at 80. If we take a look at C3, we see the same general trend. It's nice that we see the same coupling to C4 of 69 hertz that we saw in the previous slide, but again, a very large J. So we have a different situation than proton carbon. Now, just as an aside, what I want to say is that you can take an inadequate and optimize the inadequate at something like 8 hertz. And in a 1D inadequate, you can also measure long range proton coupling constants. So this is long range carbon-carbon coupling constants measured with fluorine decoupling. So we see a 6 hertz and a 7 hertz and a 2 hertz J in that thing in the middle. Well, we're going to talk about adequate here. So before we go to adequate, let's consider HSQC and what's happened to us historically. So the focus here has been pretty much on C13, where there's a perceived difficulty with bandwidth and things like that. And so lots of sequences have evolved. I just grabbed a random one out of the JEOL standard library here, where we're using Bebop 90s and Burbop 180s in here. And basically they end up for calibration compensation and wide bandwidth. So if you're not perfectly calibrated in terms of 90, it is really not going to make any difference with this type of pulse sequence. But with fluorine, things sort of turn on their head. And what we generally are all aware of course, is that the fluorine band is really very demanding. It can be far, far wider than C13. But a more troublesome part is the very large coupling constant. So a typical 1-bond fluorine carbon coupling is on the order of 250 to 270 hertz. And this is a rather enormous value compared to anything you would see proton carbon. With proton carbon, the largest couplings might be 210, 220 hertz. And those are like for heteronuclear compounds like adenosine, things like that. So we have a problem here. Now, if we take a look at adequate, in the traditional adequate experiment, I've highlighted in red on the carbon line where we need refocusing pulses. And the blue arrows say the simple inversion is okay. So we can use short, fast pulses here like BIPs, but we need something that's going to be refocusing here. To make it fluorine carbon, the key thing, of course, that you all would know is that you've got to change the decoding PFG gradient to change the ratio. Instead of like 59 something for carbon, proton carbon, since fluorine is a lower frequency, we have to up that. So it's a simple ratio of that. But a key thing is that because of the very, very large fluorine carbon couplings in this sensitivity enhancement period where the delays are not, can often be 1/6J, even with 1/4J, there is simply no time here on carbon to apply a composite chirp, which is on the order of 2.2 milliseconds. So be that as may, we can take this pulse sequence as shown for proton carbon, simply change the fluorine, fix the gradient ratio, and voila, we have fluorine carbon 1,1 adequate. run on this simple perfluoroaromatic compound. And we see all the expected conductivity. So off of C6, we see conductivity to C1 and C5. So we've got everything we expect here. It's all exciting and good. Another experiment that Josep pointed out, and this is actually far and away my favorite adequate experiment, I've been doing it for many, many years, is the NJ1J edited dual optimized adequate. It's a fantastic experiment with reasonable sensitivity considering the informational content. But if you run this experiment using the standard optimizations for it, which are really beautifully derived in the original paper done up here, they make great sense for proton carbon systems, with the exceptions of cyclobutyl and cyclopropyl, as Joonseok just showed us. So if we run this experiment with this, we see spots, and some are up and some are down, but it's not really very good. But Misha did a few calculations, and changing some delays, we could really quickly, significantly improve this experiment. It's hard to see the color, but particular of interest is that the isolated fluorine over here, F2, shows everything you would expect. We see an inverted C1, C2, and then we see long range to C4 and C10 off of that carbon-carbon. In addition, off of C6, we see a 4-bond carbon to the nitrile. So that's bridging all the way across this ring. This carbon couples the nitrile carbon, which is interesting. Of note, it's interesting to see here that there are, in fact, no connectivities observed to C6 whatsoever. And it's not in either direction, not from 6 to 5 or 5 to 6. It's an isolated carbon, doesn't show up in the long range. So the answer to this question will almost certainly be in the coupling constants and how we parameterize the experiment. So there's a lot to think about with enhancing a sequence to make it a little bit better for fluorine carbon. And I put in red here that the most interesting thing is that I did a couple of fully compensated 180 pulse programs that happened to work extremely well for proton carbon adequate, but they fail for fluorine carbon adequate and for fluoro systems. And it could possibly be from destructive cancellation from the large JFF coupling constants that are valuable. The jury's still out on this. But the most troublesome part of the sequences, the pulse programs, are the sensitivity enhancement and final inept step, where you have to be very, very careful. So in fluorine inept, we're looking at very, very large coupling constants. So the 1/4J delay time is on the order of 900 microseconds at best. The sensitivity enhancement is only 600 microtimes. So we need very short wideband duration pulses. And of course, BIPs are really very good choices, and in blue are sort of a good go-to choice I'm doing for both proton and carbon, because these fit really nicely into the short inept delays. So if we look at an HSQC that was done long ago by Haitu Hu and Krish and guys back in the Lilly days, following up on the wonderful 2001 paper describing the BIP pulses out of AJ Shaka's lab, there's a very nice construct where we could put a BIP pulse in an inept which is an inversion pulse that fixes the phase that occurs by the second one. So we can, by using pairs of BIP pulses, achieve refocusing. And what's really nice here is that these pulses are going to be on the time scale of 50 to 80 microseconds for the fluorine line. So we don't have to worry about the very short inept times. So if you're going to do inadequate, and you've never done it before, a comment I would make is if you can't, make darn sure you can run HSQC really well before you try to run HSQC adequate, because it's a whole nother level of cancellation. So this is quite true if you're doing fluorine. Make sure that however you're doing the adequate, that the same basic construct in the HSQC works well. So this is a C2HSQC fluorine carbon on Gen X of the real troublesome contaminant. We see everything that we should expect in the editing. We see the CF2 for C and B here as inverted, edited in the responses. So everything is nice. So we can make the same modifications to adequate and replace 4 out of the 6 180s with basically bit pairs here. So the first inept, the evolution, the single quantum, double quantum conversion, and then the final gradient refocusing all become bit pulses. And so what you don't see in this slide is the dramatic improvement in phase across the fluorine dimension by making these changes. So this is extremely important when you're using edit experiments that use phase to give you information. You don't want to have to be phasing your data. So this is a comparison here where the top traces in each of these are the projections from the square pulse fluorine carbon adequate, and the bottom are the improvements that we see with the partial bit compensation on it. So it's significant signal gain, even though this is not a particularly challenging bandwidth. So 70 ppm of fluorine is not all that wide. Now, you will recall that we used inadequate to measure coupling constants. And we can in fact do the same thing with Gen X. The same strategy. On the top is a carbon spectrum with NOE only. On the bottom is both fluorine decoupling and NOE. And then on the bottom is a 1D inadequate acquired with bus decoupling. So if we take a look at the boxed-in section on the next slide, you see that just picking one at random, the carboxyl carbonyl, we see that it has a 2-bond fluorine carbon of 21 hertz. There is no fluorine direct, of course. And we see the carbon-carbon coupling is 74 hertz. But as Josep pointed out here, it's a really beautiful experiment to simply drop into any adequate pulse sequence the J-modulated module. So the way I'm coding adequates these days in JEOL world is I have a simple flag. I call it J-scale. I could call it anything I want. If I check that, then this is now in my pulse sequence. This ends up convenient because I don't have to support multiple versions of pulse sequence. So I can turn the J modulation on and off. Now, it is very nice and in fact works quite well with fluorine carbon adequate. So here is a quick 1-1 adequate, and this is a J modulated result where we can measure a coupling constant. In this particular case, J scaling was set to 10. So whatever separation we see here, divide by 10, and we've got the answer. Now, we can look and do the same thing with the Gen X sample and consider the methine here, D, and we can look at the 2 couplings from it. We see an 85.5 and an 84.5 hertz coupling constant done with a J scale of 20 hertz on this. And if we go back and look against the 1D inadequate, we of course see exactly the same 2 coupling constants. But we could do this experiment in about 1/4 the time of this one. And so that's a tremendous advantage in time. So the other part of adequate that fluorine carbon has presented is the fact that if we're doing single quantum detection rather than double quantum, single quantum is advantageous because we see chemical shifts in F1, which is easy to understand. This particular delay is decremented by the incremented evolution time that's going on in T1. So this would be the line from the JEOL pulse sequence code for that delay. So the problem is that if JCC is on the order of 80 hertz, the net result will be that we're going to be limited by the maximum number of T1 increments of 40 to 60. And so sometimes the resolution requirements will need extension by prediction. Or you could use a proven computational method such as Craft2D to do this. But here's an example from that was brought out, I believe, in a previous Ivan workshop, and that is linear prediction algorithms that we've used for many years are a little bit fragile and tend to fall apart with low signal noise. And what can be more low signal noise than adequate? But what we find is that by using the NUS algorithm to do the reconstruction and extend by simply adding, in this case, I'm showing here a JEOL process list, zero field twice in front of the iterative, in front of the reconstruction. In this case, I've chosen iterative soft thresholding. We see the same data with no extension of the data and with the extension. So we see that for the chemical shift position of the CF2 here in B, we see the expected connectivities to the CF3A and the CF2C showing up, even though these particular carbons are very close together. So that's a reality that's imposed from the large carbon-carbon coupling constant. That's really a unique characteristic of fluorine carbon. So we can do the same thing. Here is a 1-1 adequate, the same data we just looked before. We're looking at this particular pair now in the fluorine spectrum. And what's really kind of nice to see here is I put the actual one-dimensional carbon fluorine spectrum on top. And you might be a little bit alarmed to see that, oh my, the fluorine doesn't line up with our correlations. Well, of course they don't. There is a bodacious isotope shift here because we're looking at, not only are we looking at fluorines that are on C13, which has a very large isotope shift, we're looking at ones that are on C13 that are adjacent to a C13, and they are further shifted. So this is a nice thing to see, but we can use the NUS reconstruction and in fact measure the coupling constants here with very high precision for these two things by dropping in the J modulation module. Now, fluorine has another problem with homonuclear couplings here. If we take a look at this CF2 group right here, it's an AB quartet, and I'm sorry for not showing these on the same Hertz scale, but there's 151 Hertz geminal coupling, and this particular one over here I'm calling CA on this position has 151 Hertz, a 7 Hertz, a 19.6, and a 1 Hertz. And there's both methyls couple these fluorines are coupled by this methyl and this methyl. So we have a real mess here. And so it makes for an incredibly spin-dilute situation. So if we look in the 1-1 adequate here and blow it up a little bit, what we do in fact see is we do see at the correct position the connectivity, one bond from this highly spin-dilute thing, but they are inverted in phase relative to the other peaks, which is not particularly surprising. We can further take a look at the J-modulated one to measure the coupling constant here. And in fact, there's only one carbon-carbon coupling constant, of course, with one adjacent C13. We see 84 Hertz measured here, and in fact, in the 1D inadequate, we also see 84 Hertz. So it dawns on me that the HD methods could possibly be of real use here in the fluorine experiment, but we have an additional challenge because at normal fluorine bandwidth, the dwell time for fluorine is extremely short, and there's not a lot of time to throw in pulses between fluorine data points. But we could restrict the fluorine observed window by pure shift and then use these pure shift methods to decouple. And in fact, the digital filters normally would totally eliminate any out-of-band signals, but we could perhaps open those digital filters up and allow some folding in F2 and recover the information. So that's really what I wanted to try to say today in a brief time. And there's a lot of people to thank, all the Seton Hall crowd, Gary and Jeff and Marius, JEOL UK, Adolfo, Paul, Michal, in JEOL USA, a number of fun key guys, and Thomas at University of North Carolina, Wilmington now. And of course, Misha and Alexei at Merck, who do so many nice things with computer simulations. closing with an update from the observatory, a little 120 millimeter scope, which at this particular time is not going to work because the shutter is frozen shut. I don't know when it's going to open again, but this is an example of a current project. This is a large object. It's about the size of the full moon, and this is a pre-supernova outburst. So this star that's sitting right here in the center is a very rare Wolf-Rayet type of star. And it's just let out a little poof. And this little poof of gas that we're looking at here is about 60 light years in diameter. So it's absolutely enormous. It's believed to be 6,000 light years away. So when it goes supernova, we hope it is 6,000 light years away. If it's closer than 2,000 light years away, we're going to have problems then that our atmosphere will be removed from our planet. So thank you very much for your time, and I will stop sharing. And
thanks, Ron. Interesting presentation. Interesting from my standpoint, even this being part of the whole project that's going on. There was one question earlier about how common one bond correlations are in N bond correlations. They are actually fairly common. When you optimize the experiment, if the one bond is in phase at the same time as whatever you've optimized for as the N bond, the one bond's going to show up. So the dual optimized inverted 1J, 1N adequate is the way to go to make sure that you don't shoot yourself in the foot by interpreting a one bond as an N bond correlation. If there's other questions, now's the time to ask them. Erica was asking about adequate with silicon instead of carbon. Erica, to the best of my knowledge, that hasn't been done. I keep pretty regular tabs on adequate publications showing up in the literature, and I have not yet seen anything on that subject.
Me neither.
yeah, silicon is a challenging case sometimes for a lot of NMR.
Yeah, it seems that we find more new challenges every day. Other questions?
Sunil was just asking, are these experiments available on the IVAN site?
At this point, there is none of this information there, but if people are willing to submit this information to us, I'm sure that we can come up with some way of getting that information out on the site.
I would be happy to share my pulse sequences with anyone.
Yeah. Yeah. Same here. A comment I would make regarding the Varian style adequate experiments that exist in TIMPAX there is that certainly the modification of that experiment to do the J modulation is really trivial extensions to the experiment. To do the NJ1J is a bit more work. I'm happy to work on it, but the challenge is, of course, if you don't have access to a spectrometer to do testing and evaluation, then it becomes a difficult task. So the problem with adequate is that unlike HFQC or some IPAP type experiments where you see meaningful results in just a few minutes, you can quickly say, I made a mistake and correct it. But with adequate, it's a whole nother situation. So a very, very careful, good choice of a model compound is useful to compress the time.
That was actually one of the criteria that defined the model compound that we used for the fluorine detected adequate. We wanted something that was simple, that wasn't going to have all of the extensive coupling that the Gen X sample has that Ron showed toward the end of his presentation. Other questions? Here's one. Why the cross peaks for 19S C13 HMBC / inadequate are not always in line with the projection. Sound difficult for the interpretation of the spectrum. Ron, you want to take that one?
No, this isn't any different than proton carbon HMBC. It's just a matter of the magnitude. If you look carefully at an HMBC acquired proton carbon and you turn off the low pass filter, you will retrieve the doublet that is the one bond. And if you look very carefully, you will see that this doublet is in fact not centered on the HMBC response. So fluorine is a bigger atom. There's more electronegativity involved here, or actually a lot of it. And so the result is the chemical shift is going to be a little bit different in a fluorine that's on a C13 carbon versus a fluorine that is on a C12 carbon. This is no different than proton. So assignments are not really any particular problem whatsoever, so long as you are aware of the situation.
Anything else? Well, I want to thank John, David, and Eric for hosting this discussion. I especially want to thank Josep, Ron, and Joonseok, wherever I'm not seeing him, but now there he is, for being able to give presentations and share their knowledge with these experiments. Steve Cheatham just posed a question: is the isotope shift the same across the spectrum, i.e., can shift the reference a bit? Question mark.
The answer is almost. It's a little bit different if it's a CF2 versus a CF versus a CF3. There's strength in numbers, and the more fluorines that are involved, the more of a shift you are likely to see. But in general, a small shift can compensate it almost perfectly.
John, let me toss this back to you, sir.
Okay. Well, I'll respond first here and ask again if there are any more questions. If not, then we'll conclude our meeting. And I'll turn it over to John, myself, for any last comments.
Thank you, Dave. And Gary, thanks much to you for leading a wonderful panel discussion today. And thank you to all of our speakers. Ron, to you for your little tour of the universe. Always exciting. And hope things get better for you in Texas, of course. My closing remark is don't forget Ivan Live from Asilomar, day before ENC, Sunday, March 28th, 10 to 3 Eastern time. And going to be a lot of fun. Be very informative and fun day. Anyway, thank you all for joining us today for yet another Ivan meeting. And always well attended, great speakers, and we're going to be continuing on this track for quite some time to come. And Dave, back to you for any additional remarks or information.
Okay, a nice picture of the next generation of NMR spectroscopists. And with that, I'll bang the gavel and conclude the meeting.
Thanks, everybody,
for
coming.
Thank you all. Bye-bye.
Bye. Thank you.
Bye.